Welcome. My name is Sue Tenney, and I am the Director of Education Programs here at NGWA. It is my pleasure to welcome you to today's Darcy lecture presentation, Fiber Optic Distributed Sensing as a Window on Subsurface Flow. Before we get started, I have a few housekeeping items. First of all, you can put any questions that you have for Dr. Becker in the chat, and we will have time at the end where we'll get to those. Also, everyone that participates in today's full webinar will receive a continuing education certificate, and you can expect that in your inbox by the end of the week. We are recording today's Darcy lecture, but the recording won't be made available until after Dr. Becker's lecture series is complete at the end of November. Also, Dr. Becker has a second lecture, How Groundwater Impacts the People and Ecosystems of the South Pacific Islands, that will be offered on Tuesday, October 29th, also at 2 o'clock Eastern Time. And once we get started, I will put the registration link to that in the chat. Finally, I would like to thank SS Papadopoulos and Associates and Woodard and Curran for sponsoring NGWA's lecture series. So, to get things started, I would like to introduce Dr. Matthew Becker. Dr. Becker is the Conray Chair in Hydrogeology and Professor of Earth Sciences at Cal State Long Beach. He holds degrees in geology and civil engineering and has worked with Los Alamos National Laboratory, the USGS, NASA's Goddard Space Flight Center, and the University of Buffalo. Matt has also been awarded Fulbright scholarships for Italy and Australia. His primary focus of research is fluid flow in highly heterogeneous subsurface environments. Matt has also given over 55 Darcy lectures already this year, with 20 more to go, and he has reached over 2,500 people with his lectures. So, Matt, with all of that, welcome. We're so glad you're here. I'll let you take it away.
Well, good morning and good afternoon, everyone. I appreciate the chance to pretend to be with you today. As Sue says, I think I've done so many of these things. It's amazing that there's anybody left that hasn't seen these lectures. So this is great that that I can reach a few more people. So I'm a hydrogeologist, and you know, I've worked broadly in a variety of areas. Started mostly with bedrock kind of systems, and then been branching out to surface groundwater, managed aquifer recharge, as you'll see, and also even geothermal. And some of that's going to show up in this talk today. The talk, it looks like it's about just a technology, fiber optics distributed sensing, and it does revolve around that. But I'm hoping that there's also some interesting hydrology in here, and that's why I say this is a window on subsurface flow. I want to focus on sort of what we're seeing with these technologies. Now, some of these technologies are relatively new, and some of them have been around for a little while, but you know, pretty much with the entire suite of these fiber optic distributed sensors, we're still very much in the discovery phase. We're learning about new ways to apply these technologies, and the technologies themselves are improving. So it's almost like we have a new microscope where we can see things that we haven't ever seen before. And so, you know, a lot of what's going on with this is we're sort of going out and making measurements, you know, with a new geophysical technique, and then sort of trying to figure out what we can learn from hydrology from that. Now, what makes these technologies particularly useful for hydrology is that in hydrology, we have this need for very time-intensive measurements, right? So we might need things that happen very fast, so precipitation events or stream flow, right? And then we have to measure that over very long periods of time, so seasons and years. And the same with space, right? Sometimes we need to look at the pore scale, and sometimes we need to look at the watershed scale, or even larger. And so it's, you know, we need both of these. We need distribution in both time and space. And what this distributed sensing gives us is a measurement technique that can approach some of those scales. And so this suite of technologies, not every single one of these technologies can go from milliseconds to years and centimeters to 100 kilometers. And so you can see that we do have some options here for making measurements. So I'm going to start with with an example that is, we won't go much into, why we're doing it. But let me start with the technology and show you how it works first, okay? So they all sort of work the same way, these technologies. You've got an interrogator, which is in a box full of, very expensive box full of technology. And this interrogator fires a light down a fiber optic cable, okay? So the laser light is being fired down the cable, and it backscatters to the interrogator, and the interrogator is using that information to measure the, well, we'll see, where either temperature, strain rate, or strain on these fibers. So it's distributed because the interrogator knows how long it takes a photon to get down the fiber and to get back. And so by chopping that time series up into very, very small gates, it can locate the signal along the fiber. And this is really the most important part of these technologies, is that they're distributed. So we can measure every 25 centimeters or meter or several meters, depending on the interrogator, over very long distances. So, 5 kilometers for temperature and 10 kilometers or even 100 kilometers or more for acoustic sensing. So what is different among the various technologies in terms of what we're measuring is how we're looking at the photons that are coming back. And so we have, for example, I'm trying to get my pointer here, right? So we're getting these signals back, and we're using the time of flight to figure out where it is. And so here's the pulse signal that's coming down, this dashed line here. And then, for example, the Rayleigh backscatter is elastic, so it's not losing any energy when it comes back. And we're just looking at the interference of those signals to make measurements. The Brion and the Raman, so we use Raman scattering for temperature. We look at the Stokes and the anti-Stokes ratios to get temperature. And the Brion allows us to get long-term strain, and we can also use it for temperature. So we don't need to get in the optoelectronics of this. I barely understand it anyway. But the point is, we're using essentially the same setup to measure all these things. And you can put out a cable that has multiple fibers and measure all the 3 of these things if you have 3 different interrogators hooked up to that cable. So let me get rid of that. Here's an example just to show you, not getting into the science just yet, but just showing what the data look like. So here's a fiber optic cable laying out in the stream in northern Italy. And we were looking at groundwater surface water interaction, which has been one of the main uses of these fiber optic sensing temperature methods. And we're also using heat as a tracer in this experiment, but what we're looking at is there's a dam upstream, and that dam releases water whenever there's a need for power. And that cold water comes rushing down the stream, and we see that, we're picking that up on the fiber optic cable. Okay, so we're using it as a tracer, if you will, coming along the stream. So let me show you what that looks like. Here is a time series where the color here is the temperature that's being measured on the DTS. And the inset here, we have the stage in the stream, and you can see it goes up and down through time as that dam releases water. And you'll see in the upper right-hand corner, there's going to be a release of water, and you'll see that cold water in blue come rushing down, right? So this is time-lapsed, obviously, but it was quite rapid. And you can see now that we have this resolution in both time and space, which gives us a very dynamic view of this flow system, of the stream system, that we normally wouldn't have. We might have just a few loggers out in the stream, and we have to kind of fill in all the other blanks. So let me show you an example where we did get something a little bit more useful, or at least we'll talk about what we get out of this. This is managed aquifer recharge. This is a really big deal in Southern California, as we need to continuously replenish our aquifers. We live in this semi-arid environment. So we get water, say, from a local stream and divert it into these spreading basins, or we buy water, say, from the Colorado River, and we recharge our aquifers that way. So these things need to be managed. They You know, as you might imagine, in Southern California, the real estate is pretty expensive, so we need the most efficiency that we can get out of these. And so we wanted to understand how this infiltration occurs. So in these basins, this basin I'm showing is a particularly small one that the Orange County Water District has. The water table is about 80 feet down. So we're looking at Vados right underneath this pond. And so the water gets spread out and percolates into the pond. And you can see that as we trench in the fiber going across this basin, you see that there's a shallow trench and a deeper trench. And we put the fiber, it goes along the surface and then in the shallow trench and then the deep trench and back. So we're just threading it back and forth. And once this is buried, it is looking at the temperature as the water moves downward. So the water is getting hot and cold every day in the sun, and we can see that percolating downward. So looking at a time series here on this graph, the black is the average of the surface temperatures, the blue is the average of the shallow trench, and the red is the average of the deeper trench. You can see the delay in time when that temperature signal shows up. So we have a phase lag of this sinusoidal signal, and we have an attenuation. This is exactly what the one-dimensional heat equations would suggest, and those little symbols on there, those circles and the triangles are showing us that the model fits the data quite well. So the thing is we could do this with a few loggers if we have some decent mixing in the basin. What we're getting out of this that's much more interesting, however, is the resolution in both time and space. So this colored plot here is, we call it a waterfall plot. You'll see a few of them, so let me orient you a little bit if you're not used to them. We have a time scale on the bottom here, and we have the distance across. So this distance across is where the cable is going across the basin. And I've taken that phase lag from the signals that you saw before for every point along the fiber, which is every meter. So we have 100 measurements across the basin. And I'm converting that to infiltration rate. So I use wavelet analysis to convert that to infiltration rate. And so the colors now are representing infiltration rate between 0 and 5 meters per day. So it perks pretty fast. The blue line here is the stage in the basin, right? So this is the water level that's in the basin. So the basin's already filled at the beginning of this data set. You can see the water level goes up and down just a little bit, like a meter, half a meter or so, and then it gets drained and then it gets refilled. So let's take a look at the data. If we look across the basin, let's look at, around 12 November 2010, and you can see that there are places that perk very rapidly in the red. You can see there are places that perk very slowly in the green, right? About a factor of 5 difference in the percolation rate. Now, if you look at the sediment here, you wouldn't predict that, would you? And it's not just the picture. You really can't see much of a difference in the texture of this sediment. So that was pretty surprising. So the places that perk well continue to perk well through time. We can now look at any position in the basin and look across through time, and you can see it starts perking very well, and then it starts to fall off fairly rapidly over the course of a few months. And this is a well-known problem in these basins. They clog. You get fines that fall on the bottom of these basins, and it clogs up the pore space, and so the permeability, the vertical permeability is reduced. So you can see that when we drain the basin, of course, the infiltration rate goes to 0, and then we refill this, and you can see that the perk rate comes back a little bit stronger. And so we wanted to understand why this is. The engineers at Orange County Water District often thought that it was because of, the cracking of these sediment layers that are in the sun. But we wanted to understand exactly why this might be happening. So we took another cable and we direct pushed it vertically into the basin. So before we were looking horizontally, this is the same basin. Now we're looking vertically. So you can see the direct push rig. The cable is very thick because it's wound cable. So we took a meter resolution of temperature and we wrapped the cable, which got it down to 5 centimeters of resolution. So now over 10 meters, we can get many, many measurements of temperature and get very high resolution measurement of that heat tracer as the water moves down. So I'm not making any calculations in this one. This is just raw temperature. And you can see where the cable is sticking out of the basin right here. See the blue and the red alternating. This is the warm California sun, just warming up that cable where it sticks out of the basin. And here again is the stage. At first, there's no water in it. We begin to fill that basin. And you can see as soon as the basin starts getting water in it, that hot and cold signal propagates downward, right? So we have distance versus time. So the slope is the velocity of the downward movement of this water. And now you can see that it's not just a constant velocity downward. The water moves downward. It gets hung up on little perching layers, so slightly finer units. And then it tends to move laterally. And we can see that because you can tell by the temperature that it's very well mixed. And then it moves down again. So we have this down, lateral. And as the basin continues to perk, we get more lateral flow. And so we have this transition from sort of vertical to lateral flow. So it's not just the vertical hydraulic conductivity, but the lateral hydraulic conductivity that begins to control the rate at which we can get water into the basin. So it's not truly perched. It's basically just being kind of backed up behind these slightly finer units. So this is actually quite interesting for the Orange County Water District, and there are a lot of management decisions that need to be made on how to manage these, and among them, just how much water to put in the basin, how much head to put on the basin, and wetting strategies and draining strategies. And these fiber optic sensing measurements can give you real-time responses for that. So let me show you another example, and this time in rock. And this is a set of experiments that we did because we're interested in how heat was exchanged between fractures and surrounding bedrock. So this is a very well cemented sandstone in upstate New York near Plattsburgh. It's the Altona Flat Rock site. And we're using it as an analog site. It's not of geothermal interest. There's no heat source here. But we want to understand how heat exchange worked. And so we injected hot water into a bedding plane fracture. And then we used the DTS to measure very high resolution what that heat exchange looked like. So why this is important is because we know that when water flows through a bedrock fracture, it tends to channel. And this is because the rate of flow in a fracture is proportional to the cube of the aperture. So a very small change in the aperture causes the water to sort of detour and go in that direction. So small asperities make a big difference in the water flow. And this channeling has a big effect on heat exchange and geothermal systems, but also, say, groundwater remediation. When you're trying to pull contaminants out of matrix diffusion, all these reductions in the contact surface area between the fracture and the surrounding rock limits that exchange. So the way we did this is we had a 5 spot of boreholes that intersected the fracture. You can see in the perspective here. Here's the bedding plane fracture, and then these are the isolated. Using packers, we can inject and pump out of these isolated zones. And then we had other boreholes that went to the top of the fracture just above, but didn't intersect it. And that's where we could measure the heat exchange. So we had many of these, and they're all being measured by one fiber. And so this is one neat thing you can do because you can measure over very long lengths. We have one interrogator. The fiber goes down one borehole, back up, down the borehole, back up, down the next borehole, back up. So you can make a network and get almost pseudo three-dimensional temperature measurements in this way. So the data are complex. So let's just take a look at the maximum temperature achieved as we pumped water into the center well, 404, and then we pumped it out of 304 in the corner, heated it, and re-injected. So we're circulating hot water. So here's the circulation in between these two wells. And what we see is that above where the water is circulating, we get hot rock, right? We're exchanging that heat quite well. And we're exchanging it using or according to sort of a dipole, which is theoretically what we would expect to happen if we have circulating wells, right? So that made really good sense to us, right? That we had for this flow seat direction, we had heating that made a lot of sense. And then we repeated this down in this other direction. So we injected again in 404, heated, or heated, injected in 404, pumped out a 104, and then back in. But now you can see that the rock, we lost one of our fibers. The rock is heating up basically in the same place that it did last time. And that's because now our flow pattern looks like this. And here is the channeling that we were worried about, that we were talking about. We're trying to push the water in this direction, and the water is going in that direction due to the cubic law, or the fact that the flow rate is related to the cube of the aperture. So let's take a look at another network system, and we're going to go back to alluvium. This is the Vandenberg Space Force Base, and there's some TCE plumes that are there from various activities that took place many years ago. And we're working with a company called Arcadis, and Arcadis has a neat technology where they try to destroy these VOCs, not by thermally destroying them, but by stimulating the biology at depth. And they do this by warming up the subsurface. So this is essentially the Arrhenius equation, just increases the rate of all chemical reactions, and it also allows the microbes to work faster. So a very general rule of thumb is about 10-degree increase in temperature, you're going to double the rate of biodegradation, anaerobic biodegradation of the VOCs, in this case, TCE. So we had a series of boreholes, and the boreholes have heat exchangers, and the fluid goes down the boreholes. It goes up to a solar collector, and that's warmed, right? So over time, we wanted to see how this warming occurred, and we wanted to see it sort of on a plume scale. We're creating a thermal plume that we hope is going to track the contaminant plume. And we want to see if we can verify that. So we direct pushed a lot of fiber into the ground. We networked them all up to one interrogator, as I showed you before. And so if you know the position on the cable with regard to depth, you can just chop this up into individual boreholes. So here again is a waterfall plot. We're going from right to left here. The heater is here and next to DTS5 and DTS4. That's a borehole heater. And so the fiber optic is picking up that heating that's occurring down here. Okay, so this is time over basically about a year. Lost the system for a few weeks here. And then afterwards, you can see enormous heating. So it gets up to about 40 degrees C. So it got quite warm here. You can see the effect of the cooler months in the spring, because the temperature the cooler temperatures drive their way downward. And then if you look downstream, so we're looking at a 64-meter transect. So now we're looking downstream at DTS7. This is 7. And you can see the heating. You can see now that the cooling at the ground is sort of affecting the heating zone, but we're heating a much broader area. You can also see that it's showing up a little bit later. And then way downstream, 64 meters downstream, you can see that the thermal plume takes months to show up, but in fact, it does warm up the groundwater, and we're achieving some heating that is stimulating the biodegradation. Now, one thing that we didn't know going into this is that even though the stratigraphy is pretty flat here, you can see that the heating is going from about 10 meters, where we want our heat to be, and slowly rising up to about 7 meters, 64 meters downstream. And that is due basically to thermal buoyancy. We didn't expect thermal buoyancy to be really an issue. And it is, we're basically, that thermal plume is drifting out of our treatment zone very slowly. So something that would be very difficult, as you imagine, if all we had was one sensor in each well looking at a time series, you wouldn't know that this was happening. All right, so that was distributed temperature sensing. Let's take a look at distributed acoustic sensing. So we say acoustic sensing, some people call it vibration sensing. But what you're really measuring is strain rate. You're measuring the optical phase demodulation is the optical term for this, between signals that are coming back from two positions on the fiber. So this is Rayleigh scatter coming back, and you look at how the photons interact at two positions along the fiber separated by what's called a gauge length. So the gauge length is a function of basically how fast you can measure those photons as they come back to the interrogator. And then you look at how they interfere to measure the strain rate. So this is a dynamic measurement. And the gauge length in this instrument, you see Thomas Coleman here from Silixa, and we have a DTS measurement and we have a DAS measurement side by side at this field site. So the gauge length here is 10 meters. And so essentially what we're doing is firing laser down. We're looking at the response from two positions separated by 10 meters. And then we do that, we step over another 25 centimeters and we do that again, okay? So you can vary the density which you want to collect. You could do it you could move the window every meter or so. But the important thing to recognize here is that we're blurring our data a little bit because we can't see any differences within this gauge length. So it's sort of like a moving averaging window on the strain rate that we're measuring on the cable. And I needed to take a moment to point this out because you're going to see it in the data. So when this technology came out, I had been working in temperature sensing, and Michael Mondanos at Alexa told me that they had this new technology where they were measuring vibration and acoustics. And at that time, I had been working with periodic hydraulic testing, and I asked him what is the lowest frequency that they could measure, and he didn't know, and really the community didn't know at the time. So we started to see if could we possibly use this vibration sensor, this acoustic sensor, to look at periodic strain on much slower scales that are good for hydraulic testing. So in other words, turn it into something of a strain meter. So we tested that by putting it into a lab experiment, and you can see the little fiber right here. So if I just strain this fiber using a stepper motor where I can control that displacement, and I plot it here, I take the integral of the strain rate through time to get just the displacement. Here's the fiber distance between 15 and 40 meters. We're only stretching this little spot right here. And you can see now the effect of the gauge length because the measurements of the strain or the displacement are kind of a top hat function. So we can't see what's going on within this little, this area in here. However, the measurement that we do get, varies slightly about depending on how we actually measure the amplitude of the strain, but we get very, very good correlation between what we put in with a stepper displacement and what we get out with the amplitude of the acoustic sensing. And so basically in the lab, we demonstrated to ourselves that we could use this as a strain meter as long as we got dynamic strain. We'll get to a technology that can measure very, very long terms, but this has to be dynamic. So we want to create a hydraulic forcing that is dynamic in if we're going to measure it with acoustic sensing. So this was a bedrock test that we first did, and this is at the Mirror Lake fractured rock site in central New Hampshire. This is a very well-known site to fractured rock hydrologists. It was developed by Alan Shapiro and Paul Shea at the USGS in the 90s, and did quite a few. I did my postdoc here, and we did a lot of experiments understanding on how the connections occur in these bedrock systems. And what we find is in these sparsely connected bedrock systems is you may get a group of fractures that are sort of connected, and that causes certain depths and certain wells to respond the same, say in this blue patch area. And then down here, these all sort of respond together in the green patch, but the green and the blue patches are not very well connected. And then the yellow and the red, so forth. These are, not single fracture features. It's just how the fractures are sort of connected up, these complicated fracture networks that develop. And this is a crystalline rock, so the fractures are small, they're sparse, they're complicated, right? Not like in a sedimentary rock where you might get bedding aligned and bedding perpendicular fractures. So what's great about this technology is you can put in these fibers, and what we're trying to do here is rather than use the pressure pulse, we're going to use the hydraulic response of the fracture to see where the fluid is going. So we don't have a distributed pressure sensor, but we have a distributed strain sensor. And so we know that when the pressure increases in a fracture, it's going to open that fracture, and we should be able to see that on these boreholes. So we coupled the fiber to the borehole by putting the fiber into the borehole, and we used an inflatable liner to push that. It's a flute liner is what it's called, the trade name, and it pushes the cable against the wall of the rock, and that frictionally couples the fiber to the rock. If we just hung it in the well, we'd get nothing, right? Because the fiber would not strain with the rock. And so we did it with all these wells. And again, we made another network. So we have one fiber going up and down all these wells. This time we measured temperature as well, but this time we're focusing on the acoustic sensing. And so we're mostly looking at these connections between 6 and 9 and 6 and 10, because those are very well known. We did tracer studies and just spent a lot of time trying to figure out just in this one zone how water flows and contaminants move. And we did tracer tests, and I'm still trying to figure out what's going on with the tracer tests. And when I die, I asked my wife that she will cremate me, inject me in FSC6 and put me out of FSC9, and then I will have my answer. But until then, we're going to try to use hydraulics. So let's take a look at what we got here. We did injection and pumping. So we pumped out, put water down, pumped out, put water down. So we had a nice hydraulic signal that was sinusoidal. And if you look at the amplitude of that sinusoid, as it shows up in these wells, here is the acoustic televiewer and the lithology in FSC9. And then these colored lines here are the amplitude of the strains that we picked up. And of course, the longer the period, 1 minute of pumping, 2 minutes of pumping, 3 minutes of pumping, the longer that amplitude, the more water we're pushing in and out. I'm sorry, the longer the period, the more water we're pushing in and out of the formation, the more strain we're going to get, right? And so you can see in this fracture zone that we already knew, we got a good strain response. Again, I'm integrating this to get displacement in nanometers. And the longer the period, the greater that strain response. And then you can see in FSC 10, the same thing. In that fracture zone, we saw a good strain response. It's a little truncated because that was the end of the liner and we didn't have any more strain measurements. But this was very well, pretty much what we expected to see. But we didn't expect this one up here, right? This at about 3 meters in FSC 9, we didn't actually know about this connection. There are fractures there, so it's not inconceivable, but the Packer testing didn't pick it up. And so here's a case where the fiber was seeing things that we didn't expect. And this gives you sort of a sense of how we could use this continuous measurement to try to delineate the plumbing, if you will, in these sparse, poorly connected fracture systems. And so if you're going to remediate, for example, a fracture system, you need first to know where the water is going. And here's a way to do this without doing individual pairs of Packer testing over long periods of time. So I want to focus on the relationship between the displacement and the period. And as the period changes, the hydraulic amplitude changes. So just looking at one depth in FSC 9, you can see here's the hydraulic amplitude, and I'm plotting that versus the displacement that we measured using the acoustic sensing. Okay. And so what's happening is, as that pressure is going up and down, we're opening and closing the fracture, and we're measuring that displacement. So you can see that, first of all, that we've got a nice linear relationship, but only on the logarithmic scale. If we plot the log of the hydraulic amplitude versus the displacement, we get a very nice relationship. And I didn't expect this. I hadn't seen this before, but it turns out it was well known to fracture mechanic folks. And what happens is, if you have a fracture that looks like this diagram up in the upper right, and there's some shear in that so that the fracture faces are not really well matched, right? So now they're just being held apart by asperities in the rock. So little bumps in the rock that are touching. It's sort of like a whole bunch of springs because the rock behaves elastically. And so as the pressure goes up and down, we're opening and closing that fracture. And that's sort of like opening and closing, plates with springs in between. Now, if those springs are exponentially distributed, as we would expect from a rough fracture, we end up with what is called the semi-log closure theory. And so this has been in the literature, and it's been shown in the laboratories and in one field test that I'm aware of. But this is the first time I've seen it over these scales, certainly in a distributed measurement. So it's kind of neat that, just from the data, we sort of presupposed what the theory was rather than trying to find data to fit our theory. So I also want to point out the scales here, which is interesting, right? So the hydraulic amplitude at the bottom end of this is about 2 millimeters ahead. And the bottom end of the fracture displacement is close to 0.5 nanometer, 500 picometers. Right. So we're looking at very, very fine resolution of strain in these rock mechanics, things that we haven't really been able to see before. And this is what I talk about when we say we have a better microscope. It's very difficult to measure these kinds of strains, even in the laboratory. So we're talking about basically displacement that is 2 water molecules wide, very, very high resolution. So let's take a look at how that strain might look in a more traditional test. So this is a slug test. And this was done at Curtin University, has a very deep well that they use. And Roman Pesner, who's a seismologist and likes to look at teleseismic using DAS, put in this fiber. So when I got down there on my Fulbright, they had this deep well with a fiber, and I couldn't help myself. I had to do some hydraulic testing. So this is a 900-meter deep well, 270 meter screen. The fiber is sort of strapped on the outside, and then it's either cemented in near the surface or it's compressed to the formation using sandpack. Okay, so it's mechanically coupled because it's outside the casing, and so we don't need a liner or anything. It's already mechanically coupled. So this well goes into a very important local aquifer called the Yargity. And one of the first things that you can see when I put in a slug, so I drop in a slug and the water level goes up, and then it goes back down. You can see in a little inset graph here. And what we see on the fiber is we see these strain responses. So right now I'm plotting strain rate, so nanostrain per second. So not integrating it in this case. And what you see is that we have places where we've got an expansion of the formation, and then we have a contraction of the formation, and they appear to be paired over very long distances. So the first thing you might notice is that in this entire 270 meters, there's only a few tens of meters that are actually taking fluid. Everything else is pretty insignificant. So this is surprising in a very, very prolific aquifer, but it turns out that there are only very few stratigraphic sections that are taking the water and storing the water. So we're looking at the pressure, the fluid movement into the formation, but we're also looking at the response and storage to that formation. So we can get a little deeper into the poromechanics of this. If we take that slug, and this is just a cylinder in the water well, and so I was moving it up and down with a winch, right? So in this case, I just put the slug in, but I can move that slug up and down, and make a sinusoidal signal like we had, for example, at Mirror Lake. And if we do that, we get a very complicated looking waterfall plot. So here you can see I've zoomed in a little bit on the just over the screen section, and you can see again the formations opening and closing, opening and closing, say along this red line, opening, closing along the blue line, but you can see that they have opposite behaviors. In some cases where you have opening formation, there are others that are paired closing formation. So if you look at that, those two depths at 732 and 773 meters on a line plot, it's very interesting because, here's the black. So this is the pressure in the well. This is the head going up and down the well. It's pretty much close to a sinusoid. And you see these strain responses in the formation. So you can see that the blue and the red, those two different depths, are indeed kind of mirror images of each other. They're opposite pairs. And you also see that the blue is following the pressure up, and then it drops off faster. And so it doesn't exactly follow the fluid going in and out. And that's telling us that there's something more complicated going on within the formation, probably leak off from these permeable systems. So, this sort of inner zone interaction is similar to what we were talking about with heat transfer between the fracture and the matrix. We often are pumping in one zone and we want to pull, say, contaminants out of another zone. And it looks like by pulsing like this, we are getting some basically vertical gradients induced in the formation. So I'm going to make a big jump to another topic, geothermal energy. Not technically groundwater, but it is. I mean, I've been doing groundwater in bedrock for years and years, and to me, this is just more groundwater in bedrock. It's just hot. So the subject that we've been working on, I've been spending most of my time on geothermal energy recently, is the idea is that there's a lot of hot rock at depth, but not a lot of it is permeable. So this is a map that's produced about favorability of geothermal resources. So that basically means shallow hot rock. And you can see, obviously, the West has more than its fair share of these sites. The yellow are where we have hydrothermal sites. So that's where we have both hot rock and we have permeability, so we can put in a hydrothermal plant. So those are traditional plants. How do we get more thermal energy out of the ground when there's no permeability to circulate water and heat it up? So let's take a look at a little cartoon from the Utah Forge site. So this is a DOE-funded research site managed by University of Utah. So the idea is you drill down into a formation, you drill a lateral so you can take advantage of vertical fractures, and you stimulate that, right? You stimulate that formation, you hydraulically fracture it, you put in a second well, and then you can inject cold water in one well, and then you pump it back out of the other well. It flashes to steam, and you generate electricity. Okay, so this is high temperature geothermal production. So one of the reasons why fiber optic sensing has become popular or useful for this is because there are not too many electronic sensors that can last very long at these kinds of temperatures and pressures, but fiber optic cable can. As long as you get it installed, which is the tricky part, it should be able to hold up to these pressures and temperature. So let me show you the results from 16A and 16B at Utah Forge. And what we have here is sort of a perspective view of those two wells. You can see the two laterals there. And the fiber is behind the casing, as I showed you in the curtain example. And then there's a little barefoot section down here at the bottom. So the cable doesn't go all the way to the bottom of the well because there's no casing at the bottom of the well. It's barefoot. And so the idea is we're going to stimulate, we're going to fracture this well, and we're going to fracture this well, and those fractures are going to connect up, and we're going to create a circulation system. What the fiber optic sensing does for us is it allows us to confirm these fractures once they're created. Now we can use microseismic, which also can be measured on acoustic sensing, to see where the rock is broken. So where fractures are created. And sometimes you use proppant to keep those fractures open. Sometimes you try to get away without it. But in either case, because of this cubic law that we talked about, because of how small apertures make a big difference in flow, it's very difficult to get a nice even flow system to develop between these two laterals. So how do you know what that flow system is that you've developed even after you created the fractures and you know they're there? Well, this is what we're using. We're using a method similar to what I showed you at Mirror Lake. We're strapping on cable onto this well. Right here, I'm showing you the temperature measurement. So at the bottom, we're at about 240 degrees C. So very hot down here. And then this is just a simulation because the data are a little too much to explain. But we have the injection well here. We're pumping water into this fracture network. We don't know in the simulation where the fractures really are. It's a cartoon kind of model. And then the water flows to these connected fractures, and where it intersects the well, we're going to get a big measure of strain. So here's our measurement of nanostrain in response to these injections. And you can see we get a very strong strain signal at this location. So we know we have a good hydraulic connection. If we have a poor hydraulic connection, say the fracture doesn't even make it all the way to the production well, we might see a response like this. And so the quality of the response also tells us something about the connectivity, and the timing is telling us about the hydraulic connections. So these tests are ongoing now at Forge, Utah. We've had a lot of problems very recently with some of the fiber optic cable failing. So it's not trivial to do this, but there have been some really good successes using the fiber optic sensing to make these kinds of measurements. Last technology that I want to talk about very quickly is distributed strain sensing. So this is using Brion, so a different wavelength of photons coming back. Typically, there are other methods, but typically we use Brion. And what we're doing is now we're looking at the photons. If we send down photons, they're going to backscatter and they're going to have slightly different amplitude and a little bit of a phase shift wherever the glass has a little bit of a dislocation in its crystal structure. And a dislocation in its crystal structure, and these are subtle things, can happen when we pull on the glass. So if we have a glass that's strained and a glass that's relaxed, we're going to get a different backscatter in the Brion frequencies. So we can use this to see what the strain is on the glass at any moment in time, and then compare those two strain profiles over very long periods. So we have this acoustic sensing that is measuring strain rate, and it's very, very high resolution into nanostrain or even picostrain. But we have to have a dynamic strain. We have to have things that are moving over the course of a half a day or less, right? And then we have this distributed strain sensing that uses Brion, and that distributed strain sensing can have very, very long time periods, but it's not as sensitive. It's microstrain instead of nanostrain. And so we're not giving up on DAS because it gives us the strain resolution, but we also want DSS that's going to give us the long-term strain. The cool thing is we can put them in the same cable, and if we have two interrogators, we can look at long-term and we can look at short-term. Both of these need to be corrected for temperature. Temperature can throw off these measurements. So we often also will measure distributed temperature sensing. So we're measuring all three. So here's an example of, this is not our work. This is a really nice work that a group out of Japan did. And so they had a pumping well, and then there was a monitoring well 7 meters away, so quite close. And they measured the strain over time. So this is strain over just a week. But these kinds of strain rates really would be very difficult to pick up on DAS because they're slow. And what you see is the drop in the strain, negative strain, as we pump, right? So it's compressing. They turn off the well, it recovers. You can see that strain response here. The green here in this plot here is the water head, and you can see at various steps the strain is basically following that, right? And then you can see that as you keep pumping, the strain increases. But notice that it's not homogeneous, right? We've got a variability in the storativity and a variability in the permeability. And so we can't separate them by just looking at this plot. But clearly the storage, because the strain is variable, the storage that's coming out of this formation is heterogeneous. And we often ignore that. We often ignore the heterogeneous nature of storativity. We just call an aquifer all one storativity, and then we look at the variability of permeability. But apparently that's not a very good guess, because we have some heterogeneity with respect to storage as well. So I think we're going to be seeing a lot of this distributed strain sensing for subsidence measurements, among other things. We have lots of good ways of measuring subsidence at the ground surface, right? And so here is a nice example in Central Valley. And this is some INSAR data from the USGS. So you can use GPS, you can use interferometric synthetic aperture radar from satellite data to get these displacements at the ground, but it doesn't tell you where that compression is happening. And what we know is that most of the water, when you pump a well and it causes subsidence, which is what's happening here in these agricultural regions of Central Valley, the water's coming out of the sands, for example, and all the compressions in the silts and the clays, right? So how do you try to mitigate a reduction in the subsidence if you don't even know which zones are actually collapsing? So you need a distributed measurement of strain. We need the vertical resolving power to be able to actually understand the mechanisms of strain. So here's a case where you can combine INSAR to get the spatial distribution and then have wells with distributed strain sensing in them. to be able to measure the strain continuously as the formation collapses. So we're testing this out now in Central Valley, and we don't have any data to show you just yet. But I'll tell you that, you know, one of the issues that you have when you do this is that you need to be able to couple the fiber, of course, to the formation. And so if you strap that cable on the outside of the casing, for example, and you get a lot of subsidence, you'll start getting slippage along the casing, and you might lose that connection with the fiber optic cable. So a lot of work needs to be done here, but clearly there's a lot of potential for getting distributed sensing from, or strain sensing from these technologies. So let me summarize, and I'll start by showing you this picture here. So this is the Water Replenishment District is putting in some wells to monitor a brackish plume near Torrance. And so we asked them to strap on fiber. And this is Hannah Fitzpatrick. She was then an undergrad. She's now a master's student. And you can see that this is really what we're talking about when we talk about installations in these water wells. You're just strapping the cable on as it goes down. And this is, in this case, it's a 1/8 inch stainless steel tube with a bunch of fiber in it. So it's not that difficult to get in. So for a very small additional costs, you know, say $5 a meter or something like that, you can get a lot of distributed data, not just in the screened interval, but all the way along the installation of the formation. And I'll also note that, like Hannah here, all of our students and all the research that I showed you today was done by master's students. We don't have PhD students. And so, you know, these technologies are approachable by master's students and undergrads. And we're having a lot of fun, basically going around strapping cable onto everything. I'm just trying to convince everybody that I can to strap cable onto their casings as they put them down. Because even if you don't have an interrogator right now, you can probably borrow one later, and then your fiber's in the ground and you can have that choice. So these are commercial systems. The interrogators are off the shelf. We're not building anything new. So they're expensive, but they're getting better and they're getting cheaper. Like any other geophysical measurement, it's not just a matter of making the measurements. We've got to understand the accuracy of the measurements, the problems with making the measurements, the interferences, signal to noise. And that's what we're spending a lot of time on now. And the only way to do that is just to have more experience with different kinds of installations. So lots of great work to be done. And I want to note that I started because of these guys. John Selker and Scott Tyler started an organization called CTEMPS, funded by the National Science Foundation. CTEMPS is still around. It just went through another renewal. And so you can get trained on this stuff through CTEMPS. You can borrow interrogators for research purposes. This organization is a great resource, and it's trained a whole generation of people to use fiber optics and hydrology. So shout out to those guys. I want to thank the National Groundwater Association for sending me on this lecture tour. I've done 55, I got 20 more to go or something like that. And every one of them has been really, really fun. Just when I get exhausted, I run into some really new, cool science or a really motivated student or brand new, super excited faculty, and I get re-energized all over again. So these are the places I'm going. I basically have this left, the Asian Australia tour left. And Sue was going to mention this, but I'll mention instead, if you're a student and you're not a member of NGWA, you should be. First of all, it's free. What's better than that, right? Not going to cost you anything. And what's unique about this organization is most of us belong to, say, GSA or AGU, or, you know, those kinds of associations. But in hydrogeology, this is the one association that really connects with practitioners, right, with industry. And it's industry that needs the problem solved. And so this is the way we keep connected to practical problems. And so I really, really encourage students that are right now in academia to get involved with NGWA. And if you are looking into going into industry, it's a great opportunity to make some connections. So I'll put up my funding sources and take questions in the time that we have. Thank you very much.
Thank you so much, Matt. We've got some questions coming in from Earlier in the talk, Gary's asking for the OCWD recharge basin example.
Yeah.
How long was each DTS reading to see the lateral movement in the vadose zone?
You mean what period of time did we look over? So we were looking for several months, and then I think we were doing 15-minute intervals. That was my memory, that we're measuring every 15 minutes. I'm not sure which one he was asking about. And that's true for the one that we had the cable vertically and the cable laterally.
Next question, what are some of the challenges in the installation of these fiber optic cables outside of the well casing?
Yeah. So I actually saw this come up as I was talking, so hopefully I covered this. In terms of this distributed strain, the jury is a little bit out on how well we can make these connections, and we're trying to learn that now in Central Valley, because DPW is getting some magnetic ring extensiometers put in where you can get multiple depths, so you get some distribution, and we're going to try and compare that to these fibers. And so coupling is an issue. It's the most important thing for mechanical measurements. For temperature, it's pretty easy because temperature diffuses through just about everything. You don't really have to worry too much. At first, we made simulations and all this stuff to convince ourselves we weren't getting all kinds of delays. But really, temperature diffuses quite quickly, and so coupling generally is not an issue for DTS, just the mechanical coupling.
So Paulo says, thanks for the talk, quite interesting. Can you provide a cost estimate for the equipment you use for this kind of application?
Yeah, there's a variety of units out there. So the distributed temperature sensing is, in the $50,000-$60,000 range or something like that. There's a lot of talk about making a more cost-effective unit because the technology is really not that expensive. It's basically, if there's enough market, for somebody to build a less expensive unit. The distributed strain sensing and the acoustic sensing, that's higher, that's more expensive. I've seen $80,000 units is probably the cheapest that I've seen for acoustic sensing, and those will go all, up to, in the $200,000 range. And then the distributed strain sensing is sort of that same range, maybe say 60,000 to, there's some instruments that are research grade that are $300,000. So you can get into this not super cheap, but when you look at the cost of, say, lab equipment, it begins to look pretty cost effective.
Nathan is asking, if you're studying groundwater surface water interactions along a reach of stream, is the relative cost of laying cable at multiple depths instead of only one going to be small compared to the overall cost of the whole system? And then follow up, are there contractors doing this work in the consulting industry regularly? He's specifically looking in the Southwest US.
To answer the last question first, I'm not aware of contractors that are doing groundwater surface water interaction, and there are very few contractors that do installations like this. And normally they're not cheap because you're competing with the oil industries to some extent. But there are companies that will come out and do installations. They'll bring the fiber, they'll do installations, they'll even make the measurements. Typically those are on well operations or engineered operations, because there's funding to make that worthwhile, because you're getting a more efficient system out of it. For groundwater surface water interaction, I have not seen that from consultants. I'm not saying that it hasn't been done. I'm not aware of it. With regard to the two depths, yeah, the cost is not an issue. A few bucks a meter or something. The extra cable is not expensive. It's the labor that's expensive, because how do you get, you got to trench it into the stream or something like that to get two different depths. So that's quite difficult. That's why most people only just lay the cable out in the stream and make a single depth measurement.
This is one of my questions. As you have been around the United States and Canada and other parts of the world talking with university students, what are you most encouraged about, or what is one thing that is encouraging to you about the future of hydrogeology?
Well, it's both encouraging and a frustration. And what's encouraging is that these students have jobs waiting for them. The market seems to be really excellent for all the students that we're producing. I've been hearing, some of the students getting recruited down into their junior year in some places where the market is really tight. And so, this is a great place to be as a student going into hydrogeology right now. The negative part is that we're not producing enough students for the consultants to hire, for industry to hire. We just cannot get them out fast enough. Most industry folks would like a master's degree, and even a thesis master's degree, and we're not getting them. We're not producing them fast enough. If you're interested in that issue, you might see Ty Foray at Arizona has been going around and speaking with consultants and universities. He's got a group called Optic, and they're trying to get together an agreement on curriculum so we can figure out how to make master's degrees maybe a little bit more efficient so that we can produce more students with graduate degrees. Most undergraduate programs are not giving the training that consultants would like to see, in their new hires. So there are a lot of other exciting things that I've seen, but I'll just mention that one.
Okay. While you were talking, a couple other questions came in. So if you've got a quick minute to
Sure.
stay on, how much maintenance does a fiber optic line require? And do you have an idea of its lifespan?
It depends on where you're installing these, right? So say you install it in a stream. If that cable comes out of the water, it's likely to get chewed up eventually. It also, I've had people go look for copper wire and cut it up and so forth. So, some of the surface applications are quite vulnerable. There are ways to get around the animal issues, and I won't go into those. But where it's in a borehole, if you're using a fiber, what's called fiber and metal tube, so you have a continuous stainless steel tube going all the way down, those are last many years. I talked to folks in Europe that have done this for dam monitoring, for example, that have been monitoring the same cable for decades. So if it's protected and you use the right cable, it has a very long lifespan. You just can't get any water into the fiber. So that has to be sealed from the fiber has to be sealed from the water because hydrogen darkens the fiber. So once you get water in that inside the cable construction, you'll lose your fiber.
All right, this will be our last question. Dave's asking, are these systems readily available to have remote telemetry for real-time monitoring?
Yeah. For example, in Vandenberg, they had a remediation system, a pumping system set up that was already wired into Ethernet. And so we were able to watch that remotely. Most of these instruments are Ethernet ready, so then you can go to some kind of telemetry system pretty easily. So yeah, pretty much all of them have that capability now.
Well, Matt, thank you so much for your time, for sharing your expertise with us. Participants, thank you for attending today's lecture. If you would like to see Matt's second lecture, you can register for that. It is on October 29th, same time, 2 p.m. Eastern time. So thank you very much, everybody. We really appreciate your time and have a great afternoon.